So the focus of our topic this week is going to be to solve exponential and logarithmic equations. To do that, we're going to need to develop a couple tools. So in video one, we're going to come up with the power, product, and quotient properties for logarithms. And these will be tools that will be fundamental supports as we move forward and try to solve exponential and logarithmic equations. So the power property is just this property here that says, hey, if we have a logarithm base b of x to the p, so we're taking x to the pth power and inputting it into a log function, that is the same as p times log base b of x. In other words, the power property says that if we have x to the p as an input into the log function, that this p, this exponent, can come down front as a product, p times log base b of x. And what we want to do is justify this. So start with the left-hand side, log base b of x to the p. And what we'll do is we'll just give this a name. We'll say, let's call this y. This is just an exponent, right? Logarithms are just exponents. In fact, this is the exponent you raise b to get x to the p. So let's give that exponent a name. Let's call that exponent y. And then we'll take this and write it in exponential form. We'll say, hey, this is the exponent we raise b to the y, to get x to the p, right? Put it in exponential form. B to the y equals x to the p. And to get x by itself, we would raise this side to the 1 over p power. In other words, we would raise it to the reciprocal of p. We would need to do that on both sides. So when we simplify, when we have one power being raised to another and we simplify it, we just multiply the powers. So we get p times 1 over p is just p over p. And this is b to the y times 1 over p is b to the y over p. And x to the p over p is just x to the first power, or x. And then you can see here we're wanting to get log base b of x. So at this point, let's take log base b of x and apply that to both sides. We'll do the same thing to both sides of the equation. I'm going to take log base b of the right-hand side, so log base b of x. And that means if I'm putting x into the log function, I need to do the same thing on the left-hand side. So we're going to take the b to the y over p and input it into the log function. And then there's a couple ways we can think about simplifying this left-hand side. One, we can recognize that log base b is the inverse function for exponential function base b. And because it's the inverse function, log base b will just cancel the base b exponential and leave us with y over p. So we could argue that from an inverse function standpoint, right? When we have inverse functions, for example, for x greater than or equal to 0, we know that the square root of x is the inverse function for x squared. And so what happens if you apply the square root function to its inverse, x squared? Well, the square root kills the squaring and leaves you with just an x. Similarly, if we take the squaring function and we put the square root into it, we know the squaring kills the square root because they're inverses and leaves us with the x. So there's a sense in which we could say log base b just kills the base b exponential and leaves us with the exponent. That would be one way to think about it. The other way to think about it would be to recognize that log base b is just the exponent you raise b to get b to the y over p. And you could say, hey, b to what exponent, question mark, b to what exponent, because the logarithm is that exponent, b to what exponent equals b to the y over p. And clearly, the only exponent that's going to work is y over p. b to the y over p equals b to the y over p. So this exponent needs to be y over p. And then once we get it here, we just multiply both sides by p. p divided by p is 1. 1 times y is y. Y equals p times log base b of x. And if y, right here, is equal to log base b of x to the p, and y, the same y we started with, is also equal to p times log base b of x, then by transitivity, these two things must also be the same. In other words, log base b of x to the p must be the same thing as p times log base b of x, which establishes the power property. Next, we want to establish that the product property, in fact, isn't magical. So the product property here says that log base b of x to the y, log base b of x times y equals log base b of x plus log base b of y. So in other words, the sum of the logs can be written as the log of the product of the inputs to the logs. So we want to establish that this is true. So the way that I'm going to do this is I'm going to give each of these two logarithms on the right hand side a name. I'm going to say, hey, the logarithm base b of x, I'm going to name it f, and the log base b of y, I'm going to name it g. And I can put each of these into exponential form. F is the exponent you raise b to get x. F is the exponent you raise b to get x. And similarly, g is the exponent you raise b to get y. So b to the g is equal to y. And notice we want to know something about the product x times y. So I'm in a great position to take and multiply x times y at this point. So x times y is going to just equal b to the f times b to the g. If I multiply x times y, that's the same as b to the f times b to the g. And I want to know something about log base b of x times y. So I might as well take log base b of both sides. So I'm going to make the left-hand side the input into the log function, and whatever I do to one side I need to do to the other. So I'm going to take the right-hand side and make it an input into the log function. And then I'm going to do a little bit of simplifying right here. I'm going to say this is log base b of, hey, I have the same base, which means to simplify I add exponents. So b to the f plus g by exponent rules or exponent properties. And then by the power property says, hey, if you have an exponent on x in the log function, you can pull that exponent down front. And right here I have the exponent f plus g. So I'm going to pull f plus g down front, and this is going to be multiplied by log base b of b. The base is left inside the log function. And log base b of b, what does that equal? Log base b of b, this is the exponent you raise b to get b. Well, what exponent do you raise b to get b? Well, b to the first equals b, so this exponent must be a 1. So we get to replace this with a multiplication by 1, which is just going to leave us with f plus g. So we have log base b of x times y equals f plus g. But what does f equal? Well, f is the name we gave log base b of x. F is the name we gave log base b of x, plus what is the name, what is g? G is just the name we gave log base b of y. So we'll do substitution to establish the result that log base b of x times y is the same as log base b of x plus log base b of y, which establishes the product rule. Finally, we'll establish the quotient rule by using a combination of the previous two properties. So we want to recognize that if we have log base b of x minus log base b of y, that we can rewrite this subtraction, log base b of x, as an addition if we multiply log base b of y by 1. So in other words, log base b of x minus log base b of y is the same as log base b of x plus -1 times log base b of y. And then once we have it in this form, log base b of x, that's a messy x, plus, and then we can say, what can we do with this? Well, this is in the exponent position, -1 times log base b. And this property here says that if you have something in front being multiplied by the log, that you can lever it up into the exponent position. So we're going to take this -1 and lever it up into the exponent position on the y. And now I have the sum of two logarithms that have the same base. And because I have the sum of two logarithms with the same base, I can combine the inputs to those logarithms as a product. So this equals log base b of x times y to the -1. And this is the same as log base b. If I want to write it without the negative exponent, I lever that y down into the denominator position using exponent properties. And that establishes the quotient property that we see here. So quick applications of these properties on 2 slides. So apply the logarithmic properties to rewrite each expression as a single term. Well, here I want to check. I have the sum of two logarithms. The bases are the same. These are both base 10 logarithms because the base isn't written. It's implied that it's base 10. And the product property right here tells me that if I have the sum of two logarithms of the same base, that I can rewrite it as a product of the inputs into those logarithms, x minus 3 times x plus 3. And I could leave it like this. I would be happy with that. I always like factored forms. You could multiply it out. If you do, this is a difference of two squares pattern, so you're going to get x squared minus 9 on the inside. I think it would be okay to leave it like this. That's up to you. Here I have the natural log. So remember that if we have a log base Euler's number of x, that because this is an important base, it gets its own name. And so the base is base e. These are two base e logarithms with a subtraction between them, so we can apply the quotient property to rewrite it as the natural log of 28, and it's a minus, so it's going to be divided by the 4, which is just the natural log of 7. Down here, a quick question is, hey, I have the sum of two logarithms. I have a sum of two logarithms. Can I use log properties to combine those into a single statement? And the answer is on this one, absolutely not. The bases don't match, which means you can't apply the log properties, which were developed using matching bases. And here you could only simplify this if b were equal to 5. We don't know the value of b, so we can't use log properties. So use logarithmic properties to rewrite the following terms as products. So here we have log of 8 to the x plus 2. We know this is log base 10 because no base has been explicitly written. We know from the power property that if we have an exponent on the number that's input into the log, that we can take that exponent and bring it down into the front position. So here I have an exponent of x plus 2. I can bring that x plus 2 down front, and it'll be log of the base. The base is 8, and now I've rewritten it as a product because this x plus 2 is being multiplied by log of 8, log base 10 of 8. This one, what I want to recognize is that the square root of 17 can be rewritten with the rational exponent 1/2. This square root of 17 is the same as 17 to the half power. Now I have an exponent on a base inside a logarithm, and that exponent can be pulled down into the front position, leaving the base behind.